Today we're going to look at one of my favorite subjects. This is grounding and bonding as it relates to three different types of installations related to grounding and bonding. One, ground fault circuit interrupters. Two, ground fault protection. And third, ground fault detection or indication. And before we get into these topics, we've got to understand how grounding and bonding works in the first place. So let's take a look at this diagram and review the principles of grounding and bonding first. The only thing that can be considered grounding in this circuit is the actual conductor that's connected to the grounding electrode. The point of grounding in a circuit is to stabilize voltages. It's to give a reference point for the transformer so that there's essentially a zero mark from where voltage knows to go up or down. This is why 10-114 tells us that our grounding conductor only has to be a number 6. The idea here is that that conductor is not actually carrying fault current. It's just providing a reference. From a theory standpoint, that conductor could be even smaller. It could be a number 14 because it doesn't actually carry any amount of current. The reason we use a number 6 is because that's the smallest size of conductor that we can bury in the earth without it being damaged by mechanical forces such as frost heave. Bonding, on the other hand, is intended to carry fault current. We size our bonding conductors by table 16, and when we're referring to bonding conductors, we're basically referring to every other conductor that's either green or bare in the circuit that does not directly connect to the grounding electrode. It's a term that's often misunderstood. Let's take a look at our circuit here and introduce a fault into the system. Let's say maybe that receptacle has a loose screw and it wiggles a bit and shorts out against the side of the box. Where's fault current going to go? Fault current wants to go back to the source, and bonding provides a path for it to do so. So when we follow that fault current path back to the source, we get back to the XO point on our transformer, and some of you are probably thinking at this point, well, fault current goes to ground. But it doesn't. Why would fault current want to go to ground through a small conductor to essentially a big-ass resistor, which is the earth? The earth is roughly 5,000 ohms per cubic meter of resistance with no path for current to flow. It doesn't make sense. Ohm's law tells us current takes the path of least resistance, and that's what bonding allows us to do. Bonding goes back through our system bonding jumper, which is the connection between XO and case in either your panel board or your transformer. It completes a circuit back through the transformer, through those nice big shiny copper conductors, and the idea is that once it completes that circuit, one of our circuit breakers, one of our overcurrent protective devices, is going to open up. Now, the code doesn't really care which one, as long as something opens up under a fault condition. But the real intent of bonding here is taking fault current back to the source. That's why not only our bonding conductors have to be sized large enough to carry that fault current, but it's critical in your installations to make sure that your bond path is low impedance, it's low resistance. You make sure you tighten down all those screws. You make sure that you remove paint underneath bonding lugs on any of the equipment that you're installing. Keep in mind that the value of these faults can be quite high. A basic formula for figuring out fault current is to take your current rating on the secondary of your transformer and divide it by the percent impedance of the transformer. So, for example, if the secondary current on this transformer was 100 amps and it was 2% impedance, our fault current would be 5,000 amps. The good news is that 5,000 amps of current flowing on the conductor should not happen for very long, because one of those fuses or circuit breakers in that circuit is going to open up to protect it. But keep in mind that fault current can be significantly higher than load current would be on any particular circuit. Now we're going to look at ground fault protection. You can find the rules around this in section 14-102. Now, this particular type of protection is for grounded systems where high energy faults can happen, but those faults aren't necessarily going to open up the overcurrent protection, the main fuses or breakers that are protecting the circuit. So when you're looking at the requirements for this rule, you'll see that it talks about systems that are solidly grounded, rated more than 150 volts to ground, less than 750 volts phase to phase, and 1,000 amps or more, or for circuits that are solidly grounded, rated 150 volts or less to ground, and 2,000 amps or more. So a few examples of these types of circuits would be a 347 600 volt circuit at 1,000 amps or more, or 277 480 volts at 1,000 amps or more. We can also see this on single-phase systems, 120 240 at 2,000 amps or more, or on lower voltage three-phase systems, 120 208 volt systems at 2,000 amps or more. Now, those systems aren't terribly common. We do come across them occasionally in rural areas where the utility can't supply us with a higher voltage. You're stuck with 240. But for the most part, I see these types of systems on 347 600 type systems at 1,000 amps or more. It's fairly common in light industrial and some commercial applications. So I'd mentioned that these types of faults don't necessarily open up the overcurrent device. The issue with these types of circuits is that when we develop a fault on these systems, the fault itself produces an arcing fault. Now, arcs themselves can act like resistors in the circuit. So if I've got a main breaker rated at, say, 1,200 amps, but that arcing fault is behaving like a resistor in the circuit, it can slow my fault current down well below the 1,000, 1,200 amp rating of that breaker and allow the fault to persist without the overcurrent device opening up. Because as we recall, fault current is going to flow back on the bonding conductor. It's going to complete a path back through the transformer, through the faulted phase, and in an ideal world, this should open up the overcurrent device, but in these types of systems with these ratings, that doesn't always happen. So the code requires this thing called ground fault protection. It's a way of sensing that a fault exists on the system and opening up the circuit when the breaker or fuse may not open on its own. The key reason we want this type of protection is that if we allow this arcing fault to persist, it's going to pose a fire hazard. It's not necessarily a shock hazard because there is a dedicated path for fault current to flow, but it definitely can cause fires, and that's something we don't want any of our systems to have. One of the systems used to achieve ground fault protection is called the zero sequence method. Now, if you've ever taken your clamp-on ammeter and clamped it around a multi-conductor cable that was under load, you'd read 0 amps, and that's because the net current flow between the hot conductors and the identified neutral conductor should be 0 amps. There's a canceling effect there. So essentially we do the same thing. What we do is we place a big current transformer around all three phases and the neutral. Under normal conditions, that CT should see 0 amps, net zero current flow, because the phases and the neutral cancel each other out. But when a fault develops, current is no longer flowing back on the identified neutral conductor, it's now flowing on the bonding conductor. So the CT sees something other than 0, which in turn sends a signal to a relay to open up the circuit. And that's how ground fault protection is achieved. Another option that works under similar circumstances is instead of putting the CT around the three phases in the neutral, we instead put the CT around the system bonding jumper. Under normal circumstances, that system bonding jumper should not be carrying fault current. But when a fault develops, fault current does flow through the system bonding jumper. So similar idea, the CT sees that current's flowing in a place that it's not supposed to. It senses that change and sends a signal to a relay, which in turn opens up the circuit.